Good day, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. In my lecture series of MSc Previous Physics, today I will deliver my lecture of Classical Mechanics, and the topic which I will discuss today is Technique of Calculus of Variation. Here we are given a function defined as f. Dependence of this function f is on y, y naught, and x. What does y naught means? Y naught is derivative of y with respect to x. Our aim is to find the function y in such a way that integral of this function between endpoints x1 and x2, it has a value extremum. Extremum means this integral can be maximum or minimum. Since y naught is derivative of y with respect to x, so y is a dependent variable. It depends upon x. X is independent variable. So since I is extremum, its variation must be equal to 0. Because variation of maximum or minima is 0. That means del I, variation from endpoint to integral from initial point to final point. Initial point being x1 and the final point being x2. We are taking integral of the function, it will be equal to 0. This del is called variation. So what we are given here, we are given that this integral is extremum, or we can say that del I is equal to 0. This is our given parameter. We have to find the path between initial and final point for which this condition is satisfied. That means we have to find the value of y for which I is extremum or delta I is 0. This is our variational principle aim. Now I'm going to derive the variational principle. For this purpose, I have drawn a graph. Since y is a dependent variable, I have taken it on y-axis, and x is plotted on the graph on x-axis. Here, this is the initial point, x1, y1, and the final point is x2, y2. Between these 2 points, we can have number of paths. I have shown here 3 paths. We can have infinite number of paths between these initial and final point. Now, to differentiate these paths, I am labeling my different paths by a parameter alpha. That means I can label them as alpha 1, alpha 2 up till the number of paths defined. Now, since y was a dependent variable and its dependence was on x, now we can say that this y will also depend upon the path. That means y has also dependent on alpha. So we have here y dependent on x and alpha. I am writing this functional dependence yx alpha to be equal to yx0 plus alpha neta x. What are these functions? Neta x is a function of x, and this function is such defined that at endpoints, that means at x1 and x2, its value is 0. That means if it is 0 at endpoints, what is the value of yx alpha? Yx0. This is our correct path. Here I have written neta is a function which vanishes at endpoints. Now, since I was a function. Integral is defined as between the limits x1 and x2, function y naught, x. Now, what was y? Dependent on initially only on x. Now, since we have defined different paths, it also depends upon alpha. So I can rewrite my integral to be dependent on parameter alpha as function y, which depends on x and alpha. Y naught also depends on x and alpha, and x is an independent variable. Now, what I am going to do in order to find my correct path, I am differentiating I with respect to alpha. And for the correct path, what will be the variation? It will be 0. On differentiating with respect to alpha, initially I am taking this first term. According to the first term, f depends on y. So writing the differential in terms of partial, it will be del f by del y by del alpha, and with the term y naught, it will be del f by del y naught by del alpha. And for the term x, it will be del f by del x by del alpha. Now, as I've already stated that x is an independent variable. So this function x, it will not depend upon the path. That means this third term, which denotes the variation of x with respect to path, this term del x by del alpha, it will be 0. So taking del x by del alpha to be 0, and since y naught is dy by dx, I am rewriting my second term, substituting instead of del y naught, dy by dx. Now I will solve this second term by integrating it by parts. Since there are two terms, I am taking this as first term and this to be the second term to solve my integral. We know that when there are two terms in the integral, we have a formula, first term outside, integral of second minus differential of first and then integral of second. Solving this by using this formula, first term is del f by del y naught, this term as it is, and integral of this second term, as I am integrating with respect to dx, so differential and integral cancels, so I get del y by del alpha. And the limit is x1 to x2 minus integral differential of first term, that means d by dx, del f by del y naught, and we have already solved the integral of second, which is equal to del y by del alpha. This is the second term of this expression. Now I am using both these expressions. So my partial differential of I with respect to alpha, it will become first term del f by del y by del alpha. This is the first initial term. Now, what is in this term? I have del y by del alpha at endpoints. I have to find out the value of del y by del alpha. As I have already defined y function, differentiating with respect to alpha. What will be the differential of y with respect to alpha? This term contains no alpha, so its differential will be 0. So differential of y with respect to alpha will be equal to neta x. And what is neta x? It is 0 at endpoints. And in this expression, I have to find the value of del y by del x at endpoints. So this term will be equal to 0. So in this expression, I have only two terms. First is this and another term is this value. I am collecting all the terms. This is the equation. Here in these two terms, del y by del alpha is common. So I have taken it outside. Now I am multiplying both sides of this expression by d alpha. So multiplying both sides by d alpha, I have multiplied simply by d alpha. Now here I have variation of y with respect to alpha. And when this variation is taken with d alpha, this denotes delta y. And similarly here, this term denotes delta I. That means increase in the integral as I am moving from my correct path to comparison path. Suppose this is the correct path and all these paths, they will be the comparison paths. Delta I denotes, suppose I am taking this path, this first path, then delta I means variation of this correct path with respect to this path, which I am now taking. So moving over to my integral term. Here I am rewriting my expression to be del I integral x1 to x2 del f by del y minus d by dx del f by del y naught. Del y, variation del y dx to be equal to 0. Since we have already given that integral I is extremum. I is extremum, that means del I must be equal to 0. This we have already stated in my variational principle statement. So substituting it to be 0, I get this equation to be equal to 0. Now the variation del y, this represents arbitrary variation of y with respect to alpha. As we can take any path, so this variation is arbitrary. So this bracket term can be substituted to be equal to 0. So students, this is the condition that y must follow for integral to be extremum. The condition is del f by del y minus d by dx del f by del y naught, this equal to 0. This is a very important condition that we must remember for integral I to be extremum. Here f is a function of three quantities. What are these quantities? X, y, and y naught. X is independent, y is dependent, and the dependence is on parameter x. I hope students, you must have learned what I taught you today. Thank you students for watching.